Okay, great. So welcome everyone, and it's a great pleasure to have Fermi Ma to speak to us today. So Fermi did his PhD at Princeton with Mark Zandri, and then he moved to the Simons Institute as a postdoctoral fellow, where he is now. And interestingly, he got interested in quantum. So his PhD, he mostly focused on classical crypto, but then during his the last part of his PhD and increasingly in his postdoc, he's been working on quantum crypto at this intersection of quantum and crypto and classical crypto, which has been really interesting. And he's contributed a lot of beautiful insights into it from his work on rewinding, quantum rewinding, to prove the correctness of classical protocols against quantum attacks, to his work on quantum commitment schemes. And today, what he'll talk about is I should say that this is really very elegant, very an amazingly relatively simple proof of something that has been attacked by much more complex techniques. So Fermi, looking forward to your talk.
All right, thanks so much for the introduction, Imesh.
Sorry, we can't hear you.
Oh,
Are you muted? No. Oh, sorry. Okay, it's okay. Sorry, my fault. Yeah, go ahead.
Slides looking good?
Yeah.
Okay, great. All right, so thanks so much for the introduction. Today I'll be telling you about this work called How to Construct Random Unitaries, and this is a joint work with my wonderful collaborator, Robert Huang. And so I just want to start by defining the Haar measure, which is the unique unitarily invariant measure or distribution on SU 2 to the n, which is the space of unitaries on n qubits. And what I mean by this is that it's like the unique distribution on unitaries with the following property, that if you fix any unitary W and you sample U according to the Haar measure, then W times U is also distributed as a Haar-random unitary. So Haar-random unitaries show up in basically every corner of quantum computation. So let me not even read this list off to you, but they're really showing up everywhere from complexity theory, cryptography, physics, fundamental questions in quantum information theory, various practical questions. And to sort of pull a quote directly from a Quanta article, the general philosophy behind all this is this surprisingly powerful principle that kind of holds true all throughout math and computer science, which is that kind of whenever you have some task or some phenomena you want to understand, it's often a surprisingly good idea to start by trying a random object, and sort of unitaries are no different. So one major challenge, though, is that Haar-random unitaries are kind of by their nature exponentially complex. So what I mean by that is that if you take a Haar-random unitary U, and you look at the minimal circuit that implements U up to some precision, then almost certainty, this circuit has exponential depth. So exponential in n the number of qubits. And so this is quite problematic because it means that even if you show that a Haar-random unitary with some very high probability solves whatever problem or task you have at hand, this often isn't good enough, right? In nearly any application imaginable, you're not going to be happy with an exponential time solution. So this motivates the notion of a pseudorandom unitary, or PRU for short. So a PRU, pseudorandom unitary, is a efficient set, or is a set of efficiently computable quantum circuits. Like a set of U sub k's, so the k is going to be some key, and the key is indexed into the set, with the following guarantee, that for any quantum polynomial time algorithm A, it cannot distinguish the following two distributions. The first being a unitary sampled at random from this set of unitaries U sub k. So you pick a random key and then you fix that unitary. Or the other where you sample the U uniformly at random from the Haar measure. And so this quantum polynomial time algorithm has the ability to query this unitary U, sort of run it on any state it wants, get the output state, and kind of repeat this as much as it wants, as long as it's still running in polynomial time. And at the end, it has to guess which distribution it was given, either the Haar-random unitary or the PRU. So again, a PRU is an efficient family of circuits with this guarantee, that no efficient algorithm can distinguish them. And for those of you who are familiar with classical crypto, the PRUs are kind of the unitary analog of a fundamental classical cryptographic object, pseudorandom functions, or if you want, pseudorandom permutations. So obtaining a provably secure PRU has been a central open question ever since the notion was first proposed. There's actually been quite a number of candidate constructions. So in the original work proposing the notion of a PRU, Ji, Liu, and Song, there's this conjecture that perhaps if you interleave queries to like a random function with Hadamard to change the basis, that eventually, like after some point, this becomes a pseudorandom unitary. And since this original work, we've seen a number of other candidate constructions. One more that I want to highlight in particular here, this PFC construction, which is going to feature pretty heavily in today's talk, where the P is a random permutation applied in place, the function is a random function applied in the phase, and the Clifford is a random unitary drawn from the Clifford group. If you didn't catch all that, don't worry. When we need this distribution, I'm going to define it a little bit more carefully. And these are not the only candidate constructions. A number of other works have also proposed different candidate constructions of PRUs. So before this work, the state of the art, the best we knew about these candidate constructions, or I should say some of them, is due to a pair of works by Mecker, Paremba, Sinha, and Yuen, and Chen, Bullen, Brandau, Dr. Hayden, and Xu, where they showed how to obtain pseudorandom unitaries that are secure against a class of algorithms that make non-adaptive queries. So in particular, if your algorithm has this form, where it performs some initial layer of computation, and then it performs all of the queries to the unitary in parallel, and then after this never queries the unitary again, then against this class of algorithms, we did have PRUs that were secure. And this is actually like a fairly useful class of algorithms. Like for a number of applications, this is actually already enough. However, the general question of PRUs secure against arbitrary polynomial time quantum algorithms remained open. So before I talk about what we do in this work, I want to say one thing about, in my opinion, why it's been hard to prove PRU security. 1 second. So in my opinion, one reason for this is that we lack what I would call user-friendly techniques for analyzing Haar-random unitaries. So when you're trying to build a PRU or trying to prove security of a PRU, at the end of the day, you have to prove a statement that looks something like this. So let me call the state ket AU, the final state of a quantum algorithm that has queried some unitary U some number of times in whatever way it wants. Ultimately, you have to prove something about the following two density matrices. The first being the mixed state you get when you choose U at random from the PRU family, and the second being the state you get when you choose U from the Haar measure. And actually, like no matter what PRU construction you have on hand, you do have to like find some way to say something about the second density matrix, which is the density matrix you get when you sample a Haar-random U. And already this is something that's pretty hard to work with, particularly like bounding the moments of Haar-random unitaries is like a notoriously hard problem. It's often quite involved. And typically this is done by employing techniques from representation theory, things like the Weingarten calculus, maybe free probability. And these techniques can be quite cumbersome. So what do we do in this work? Our main result, we show that PRUs exist. In particular, we analyze this construction of Mecker, Paremba, Sinha, and Yuen. We show this PFC construction, permutation function Clifford, is secure against all quantum polynomial time algorithms. And this is under the assumption that one-way functions exist. And what I really want to highlight is how we do it. And it's with this new technique we call the path recording oracle. So I'll spend a lot of this talk explaining this. So don't worry if the slide doesn't make sense right away. But basically what this is a new way to analyze. Yeah. Is there a question?
No.
No. Continue.
This is a new way to analyze random unitaries using kind of quantum 101 technique called purification. And along the way, like one consequence of sort of how our proof works is we also show the following fact that, as stated, actually has nothing to do with PRUs. It's a sort of information theoretic fact that any quantum algorithm that queries a Haar-random unitary U can be efficiently implemented to inverse exponential error. In fact, we actually go one step further. If you look at the original definition of a PRU in Ji, Liu, and Song, the way that the algorithm, the distinguisher that queries the unitary U, the one that's trying to distinguish the PRU from the Haar-random unitary, the way that you model it is you give the distinguisher access to the unitary U, but you don't give it access to anything else. Particularly, the distinguisher doesn't have access to the inverse unitary. I think in many settings, it's like quite reasonable to imagine that your distinguisher might have access to the inverse unitary. Like for instance, if you have any implementation of a quantum circuit, you can always sort of gate by gate invert it. And indeed, like many quantum algorithms that we think of as sort of making black box access of some underlying unitary, like if you look under the hood, they're actually querying both U and U inverse. This is like a pretty common practice in like quantum algorithms. So just to be clear, like the standard notion of a PRU distinguisher in the Ji, Liu, Song definition, these algorithms that look like this, that only have U gates. Whereas you can imagine a stronger notion of a PRU being one that's secure against algorithms that have access to both these U and U inverse gates. And so that's our second result. We prove that strong PRUs also exist under the same assumption that one-way functions exist. And it requires a slight modification of the construction that this permutation function Clifford construction, you're actually going to have to put a Clifford on both sides, which is, in hindsight, not that surprising. It turns out that this strong PRU result is considerably harder from a technical point of view than the standard one. And for most of this talk, I'm just going to focus on the intuition behind our standard PRU result. Right. So actually, most of this talk is not even going to be about PRUs explicitly. It's going to be about this idea of efficient simulation, or rather efficient simulation of Haar-random unitaries. And if it's not clear what I mean at this moment when I say like efficiently simulate a Haar-random unitary, that's going to be kind of something that I hope to cover in the first part of this talk, where I'm actually going to put unitaries aside entirely and just talk a little bit about what it means to efficiently simulate a random object. In particular, we'll start with the example of a random function. And that's going to sort of give us the intuition, notation, some of the tools to understand how our simulator works for simulating a Haar-random unitary. And finally, at the end of this talk, I'm going to tie this back to PRUs. And I'm actually going to do two proofs at once. One, I'm going to prove that our simulator actually works, that this like simulator that I'll define in part 2 is actually simulating a Haar-random unitary. And at the same time, in the course of that proof, I'm also going to show that PRUs exist. Okay, so that's the plan. So for the next 10, 15 minutes or so, I'm not going to talk about unitaries though, and I'm just going to start by exploring like what is efficient simulation and what does efficient simulation of random functions look like. Okay. So as a very basic warm-up, imagine you have a classical algorithm A, and it queries a random function. So this classical object F, so random Boolean function. And the sort of standard, like naive way to run this algorithm is you literally just sample the random function at the beginning. This takes exponential time. You have to fix the entire truth table of a random function. And every time the algorithm queries a function, you literally just respond in the obvious way. You just give the value of the truth table of that function at that point. Now, there's another way to run such an algorithm, which is the efficient simulation. And the way this works is as follows. Instead of, you're actually not going to sample a random function at all. You're going to start by initializing an empty set R. And what you'll do is every time the algorithm queries on some input X, if X hasn't been queried before, you simply just make up an answer on the spot. So you sample a random Y, you give that back to the algorithm, and then you're going to store this ordered pair XY in your set R, and you're going to store it for later. So, and the reason you want to store it is in case the algorithm queries that same X again, in which case you want to look up that ordered pair and return the Y that you returned before. And this is just because in the random function case, like the function's always going to return the same output on the same X. So this is called on-the-fly simulation, and sort of technique used all the time in cryptography. And what this gives you is this polynomial time way to run an algorithm that queries a random function, or a classical algorithm, I should say, that queries a random function. And one thing I should know is like this is a stateful procedure, right? You need to maintain this state, this list of ordered pairs that you've sampled so far. So now, sort of to bridge the gap between talking about random functions and these classical algorithms to eventually where we're going to go, I want to ask, like, what if this algorithm is quantum and essentially queries a function in superposition? So now A is this like quantum computer, this random function, and instead of being restricted to just asking the function like what its evaluation is on inputs x, now A can ask on a superposition of inputs x. So it can query on a sum of superposition over x of like alpha x ket x. And I'm just going to model this. I'm going to model the way that this oracle returns its answers as placing the answer into the phase. So this is the sort of standard oracle or a phase oracle encoding of a function. So on every ket x, it's going to pick up a phase either plus or minus 1, depending on the value of the function at this point. And so this is the state the algorithm expects to get back when it makes a superposition query. And the problem with this setting is that now it's not so clear how to sample f of x on the fly. And kind of the intuition here is that like the way the simulator I described in the previous slide worked, it seems to require knowing x. Like for instance, you have to at least know if x was sampled before or not. But naively, like measuring x is going to destroy the superposition. And that's, if you look at this picture, that's not what's happening here. You have to return the answer kind of and preserve the coherence of the superposition. So the solution to this is something, is a very influential work of Mark Zandri, proposing this idea of what he calls the compressed oracle. And in hindsight, the compressed oracle is really like the right way to generalize this basic simulation strategy in the classical algorithm case to the case of quantum algorithms. So let me tell you about how the compressed oracle works. Okay, to define the compressed oracle, it's going to be this linear map, we'll call it CO, and it's going to act on two registers. One is this ket x state, and this ket x state is just the input state, so it's the n-bit string that the algorithm wants to query on. But it also has this additional register that I'm going to color in light blue. And this additional register corresponds to some like purification state, some like hidden environment state that the algorithm is never going to see. And this ket R state, R is actually going to be a set. So R is going to contain a set of these x1 up to xt. And just to make sure everything is clear here, when I write a set inside of a ket, like I'm just indexing a quantum state by a set. And this is really no different from indexing a quantum state by an n-bit string. Okay, so when I write the set inside of a unit vector, you should think of it as, well, if I have two unit vectors, ket R and ket S, then they're going to be orthogonal if the sets are different, and they're going to be parallel if the sets are the same. Okay, so nothing crazy is happening here, but it's just like mathematically convenient to index these states by sets. And so what does the compressed oracle do on an input of XR? By the way, I should say that I'm describing a quantum algorithm that acts on like arbitrary superpositions, but it's going to be enough to specify the algorithm by just telling you how it acts on a set of orthogonal basis states. So that's what this slide's going to do. Okay, so what it does on XR is going to map it to X and then the set R symmetric difference of the singleton set X. So in particular, if X is not in the set R, it's going to add it to the set. And if X was already in the set R, it's going to remove it from the set. So that's how the compressed oracle acts. And you should think of this as like intuitively, it's recording X onto this R register, but in such a way that, if X was already recorded before, it's going to delete it. It has to erase it somehow. And so what this compressed oracle does, the sense in which it simulates the queries of the random function is the following. That if you look at these two different ways to run a quantum algorithm that queries a random function, so on the left is kind of the standard way of running the algorithm where it queries this oracle O sub f, where O sub f is just the sort of standard phase encoding of a random function. So O sub f, when you apply it, just puts the value of the function into the phase. If you look at that on the left as as producing some state like A sub f, and you look at the state on the right, and you compare the following mixed states. Particular, you compare the state that you get when you pick a uniformly random function f. So that's expectation over f of this AF state. And you compare it to this mixed state rho. And the reason that I have a row on the right, mixed state row on the right-hand side is because I have a global pure state if I look at all of the registers, but then I'm going to trace out the purifying register. And so what I'm going to have left is a mixed state. And the claim is that this compressed oracle gives you a perfect simulation of the algorithm's mixed state when it queries a truly random function f. So again, I want to emphasize like the state on the left, this expectation over f of ket bra af, like that's a mixed state because the function f is like a classical random object. And on the right, I have a mixed state rho and that's mixed because I have a pure state and then I'm tracing out part of it. I'm discarding part of that pure state. So I don't want to say too much about how exactly you derive this, but I want to say it's not too hard. Actually, if you look at Mark's paper, it's basically like a one-page, like a few paragraph long derivation. Kind of the gist of it is, or the key idea is really you replace the random function f with a purification. So instead of having this expectation over a classical random f, you instead consider this uniform superposition over all possible choices of the function f. So now like this ket f is an enormous register. It's exponentially large. It has to have the whole truth table of a function. And you consider the superposition over all possible choices of f. And you look at this like global like purification state. And the whole idea is really to look at this ket f register in the right basis. In particular, in Mark's case, it turns out to be the Fourier basis. And so I don't want to say too much more, but if you look at what each query is doing in the Fourier basis, and you kind of squint, you'll see that really like what it's doing is precisely this compressed oracle. By the way, if that didn't make total sense, don't worry, we're actually not going to kind of build off this particular proof. But I just wanted to give you kind of a taste of sort of where this comes from. So before I go on, I want to say one more thing about like how I'm going to think about what Mark's work says. Because in some sense, this work is actually showing you how to simulate queries to a certain kind of random unitary, particular random diagonal unitaries, right? So these OFs that the algorithm is querying, I mean, they're writing the function to the phase, and you can think of it as really just querying a unitary oracle, but the unitary corresponds to this diagonal matrix of plus and minus one. Like that's exactly what a phase oracle looks like when you turn it into a matrix. It's actually plus minus one just because it's a Boolean function. But if you were to write down a compressed oracle for a many-bit output function, you'd actually get something that has these more like finer grained complex phases. So really like think of the compressed oracle as handling random diagonal unitaries. And this work, what we're going to do is simulate queries to Haar-random unitaries. And Haar-random unitaries look quite different from random diagonal unitaries. And kind of one important distinction here, and part of the reason why at least the same approach used to derive the compressed oracle is not going to work for random unitaries, is that the argument, like under the hood, the way you arrive at compressed oracles relies very heavily on the independence of the entries of these of this random diagonal unitary. Like in particular, like every diagonal entry is like uniformly random and independent from each other. Whereas if you look at the entries of a Haar-random unitary, like the fact that it's a unitary like forces the columns to all be orthogonal to each other. And that makes it so that the entries are not actually just independent random variables. So that's kind of one of the challenges that somewhere along the way you need to resolve. Okay, so up next, I want to define or describe our path recording oracle, which is going to be the object that we show will simulate Haar-random unitaries.
So for me, I don't know if you take questions in the middle or after. I don't know.
Oh yeah, if there's questions now, that would be
great. But it should be true that if I only look at a few entries of you, they should look like IID random, right?
Yes. Yeah,
it's a proof,
it is true, and this has been formalized to varying extents in the literature. It's just not clear how you kind of go from that to, let's say, sort of directly trying to extend Mark's argument or Mark's purification proof to random unitaries. Like, you can take his steps where you purify as a random function and write down the analogous thing for random unitaries. It is just not clear what to do next.
Okay, thanks.
There's no questions from the audience or anything. Also happy to be interrupted at any time for that. Okay, Okay, maybe I'll go on.
Sorry, and then what would happen to the off-diagonal entries if let's say that you were to take that approach? Would the off-diagonal entries pose a particular challenge, or do you think that the diagonals are the most important piece?
Oh, I guess I'm not really drawing much of a distinction between like the off and on diagonals. Like, I mean, there are some senses in which random unitary, like Haar-random unitaries are, morally matrices of random, like IID random complex Gaussians. But sort of like the overall like spectral statistics will be quite different. And I mean, you could show that maybe like any 2 entries or any like 4 entries sort of behave independently. But typically when you consider these algorithms that are querying the whole unitary, you're going to have like exponentially many terms to consider. So it can be quite tricky to kind of deal with this like almost independence. But I'm not saying it can't be done. I mean, this work is doing something. So I'm just saying it takes a little bit of care. Okay, so I'm going to describe our path recording oracle, and it's going to be kind of the object that is the analog of the compressed oracle, but for simulating Haar-random unitaries. And this path recording oracle, like throughout today, I'm going to abbreviate it as PR_O. And just like I did with the compressed oracle, I'm going to tell you how the path recording oracle works by just showing you what it does to a set of orthogonal basis states. And again, the orthogonal basis states are going to be these ket X tensor ket R states. But now this R, it's still going to be a set, but it's actually going to be a set of ordered pairs. So not just sets of like n-bit strings, but actually ordered pairs of 2 n-bit strings, xi, yi. And again, like when I write a set inside of a ket, it's still the same thing. Like 2 set states are orthogonal if they're actually different sets. And the result, though, looks quite different now. So when you apply this path recording oracle, the ket X, ket R, the resulting state you get looks like this. It's going to be this superposition over all the y's that are not in R. So what does it mean for y not to be in R? It's just my shorthand for really saying that I want to sum over all the y's that haven't appeared as like the second element as one of these yi's in the set R. Okay. So I'm going to have the superposition over all y's that have not yet appeared in my set R. And the state I have is going to be ket y tensor R union the singleton set xy. So I'm taking a superposition over all the y's, except the ones I've seen before. And kind of in the branch where I have ket y, I'm going to add this ordered pair xy to my set. Okay. And let me just say, like, actually, just because I didn't have space on this line, there really should be a normalization term in front. There should be some 1 over square root n minus the size of r in the front. Because I really do want this to be a unit vector. And it's going to be important that actually this PRO that I've defined is an isometry. Like it's like a physical, like actually efficiently implementable linear map. And so I'm not going to prove that it's isometry today, but kind of the intuition for like why you should at least believe me is, I mean, so what does it mean for it to be an isometry? It means that if I start with 2 orthogonal states, like XR and like a different X prime, R prime, that they get mapped to orthogonal output states. And the intuition for like why this should be true is that if you look at the form of like of this output state, you look at these individual like y and then r union xy, like that uniquely determines x and r. In particular, like if you have this y separate like y and then a set r union xy, we know that because this y has not appeared anywhere else in R, that you can uniquely look up the corresponding value of x. So that's why this restriction that we're only summing over the y's that haven't appeared before in the set R, like that's where this comes in. That is what guarantees that this linear map I wrote down is actually an isometry. So in the past, I know that like kind of sort of putting up this definition gets pretty confusing. So maybe I'll pause for a moment and just anyone has questions and kind of parsing what this is saying. This is sort of the fundamental object that we're going to study for the rest of this talk.
So can I suppose just a syntactic, I'm just trying to parse, right? So if R contains a pair of the form x comma y, If R doesn't contain a pair of the form x comma y, this is going to be a superposition over all y's and R union x comma the corresponding y.
You mean if R is an empty set?
If R is an oh, so y being in R means that there exists an x such that
Yes. Yeah.
okay, I see. Got it. Okay.
Yes.
Good.
Yeah.
If not, I would pick out the y's that don't appear and then sort of associate it to x.
Yes. Yes, exactly. And that's why like y together with
That's why
R
it's
y
yeah.
uniquely determines XR.
Got it.
Yeah. So this is the definition. It's hurts your head a little bit to kind of grok, but
it's sort of like it's sort of like you're trying to simulate a permutation, a random permutation.
Yes.
Right?
Yes, exactly. If you were to simulate a random permutation, it would look almost exactly like this, except it wouldn't be a superposition. It would be just a random y. You would be picking like a random y that hasn't been used before, but you would be like picking a random y and then adding this tuple xy to the set.
Right, classically. But if I had a quantum access to a sort of a quantum access to a permutation, a random permutation,
yeah,
you would need to do something like this, right? Or maybe not. Okay, I'll take this offline.
Yeah. No, there's absolutely like strong parallels to random permutation and simulating random permutations. Yeah. But the simulator for random permutations would not be exactly this. It, I guess, has to be something a little different. Okay, so the claim or the sense in which the path-according oracle simulates random unitaries is exactly the same as the sense in which the compressed oracle simulates random functions. So in particular, if you consider two different ways to run a quantum algorithm that queries a random unitary, the left being the standard way of running it, where you sample a Haar-random unitary and then just run the algorithm as it expects to be run. And the right being where you replace every call to the random unitary with a call to this path-according oracle object that acts on both the algorithms, like the oracle query register, as well as this hidden external register. And that external register is initialized to the empty set. So that's what this null thing is denoting. Then the following two states are close. So one is the state on the left when you average over a Haar-random unitary U. And the state on the right, which is just the mixed state you get when you trace out this purifying register. I should say that while the simulation in the case of compressed oracles is perfect, here we actually have a little bit of error. In particular, the trace distance between this row and the state you get on the left, this expectation over the Haar measure, the trace distance is inverse exponential. In particular, it's t squared over 2 to the n, where t is the number of queries your algorithm has made.
Sort of like a birthday,
yeah,
object.
exactly. Yeah, and it comes from birthday,
birthday. Yeah.
Yes. Yeah. Okay. Good. So we're going to spend a good fraction of the talk actually sort of diving into how we prove this. But before we do that, let me just give you a little more intuition for the fact that this is even plausibly true in the first place. So let me do just a couple examples. So the first example is going to be the easiest possible example. You just make a single query to the Haar-random unitary, and you query it on the all zero state. So in the standard execution where you query a Haar-random unitary, your output state is U applied to 0. This is just a Haar-random state. And then when you average this over the Haar measure, what you're going to get is the maximally mixed state. So now I want to show you that you're going to get the same thing when you query this path recording oracle. So if you make one query to the path recording oracle on the 0 state, well, remember the purifying register is initialized to the empty set. And let me remind you the definition of the path recording oracle here at the bottom of the slide. So applying this definition to the initial state of 0 together with the empty set, you're going to get a superposition over y. Actually, you're going to get a superposition over all y because R was the empty set, so there's no constraint there. And the state you get is ket y tensor, a singleton set. And the set just contains the ordered pair 0, y, right? Because it's storing x, y, and x was initially 0. And what the algorithm is going to see is actually the results after you trace out this blue register, the set register. And what is the set register containing? Like, what's the information in that state? It's just y, right? The 0 isn't doing anything. And so it's like you're taking this maximally entangled state, sum over y of ket y tensor ket y, and then just tracing out half of it. And that's going to give you the maximally mixed state. So these two actually in one query are exactly the same. Okay, so let me do a slightly less trivial example. Let me do two queries, both on the 0 state. So kind of two parallel queries on the all 0 state. And in the standard execution, you're going to get U0 tensor U0. And when you average this state over a Haar-random unitary, you're going to get a state that is maximally mixed, but not maximally mixed over the whole space, but it's going to be maximally mixed over a certain subspace called the symmetric subspace. And this is, you haven't heard this before, this is just the linear subspace of quantum states that is spanned by all states of the form psi tensor psi. Okay? In other words, like these are the states that pass the swap test. So over this subspace, you get the maximally mixed state. This is just kind of like a basic fact about Haar-random states. So let's see what happens when you query the path recording oracle. So here, if you make two parallel queries on 0, then what's going to happen is in the first query, the path recording oracle acts on 0 and the empty set. And the second, it's going to like ignore that first wire. It's going to just carry it through and act on the second 0 and whatever set you had after the first query. And if you just plug in the definition of the path recording oracle and you look at the state you get at the end, now you're going to get a superposition over all distinct y1 and y2. So you're going to get ket y1, ket y2 on the two registers the algorithm can see. And then this is going to be in tensor product with a set of size 2. In particular, the set is going to be the set of the ordered pair 0, y1 and the ordered pair 0, y2. So this is if you don't see it, maybe just trust me. This is what you get when you plug in this definition. And what's going to happen again is you're going to trace out the set register. And what the set really is containing, you can again sort of safely ignore the zeros. And this is really just a set that contains y1 and y2. And so when you trace this out or measure, what you're going to get left on the algorithm register is, let's say you measure a set y1, y2. Well, the algorithm state is going to collapse to the superposition of states consistent with that measurement outcome, which is going to be y1, y2 plus y2, y1. And it turns out that this mixture over y1, y2 plus y2, y1 for a random choice of distinct y1, y2 is like incredibly close to the maximally mixed state over the symmetric subspace. Turns out like these vectors are nearly a complete basis for the symmetric subspace. We're just missing a few vectors that only contribute sort of a negligible error.
What are these vectors? Are they y comma y's?
Yes, yeah, exactly. The only ones that I'm missing are the y comma y's, the ones where there's actually those vectors. They're also in the symmetric subspace, but this mixture is not picking them up. But sort of intuitively, right, you would have capital N of those and like order capital N squared of these guys. So they kind of get washed out.
So again, the reason you're not able to subsume even that and get a perfect simulation is because of the isometry, because you want this sort of like, this mapping at the bottom of the page to be an isometry, right? That's why you
they're actually there's no like fundamental reason why you shouldn't be able to have an exact simulation. And in fact, there is a prior work of, I think, like Logic and others that sort of describes like how one might write down such a simulation, like an exact simulation. I'm not sure like how explicitly they write it down, but they at least say that like a space efficient simulation should exist. It's not clear to me if like a actually efficient one exists though. But sort of intuitively, if you kind of think about how much of the randomness of a Haar-random unitary the algorithm gets to see at each query, you can kind of convince yourself that like a space efficient simulation must exist. Maybe let me go into this later or something, but yeah, that is a totally reasonable question of like, why exactly are we picking up any error at all? Yeah. Okay. So if these examples make sense, then I want to go ahead and kind of as promised, actually convince you that the simulator is simulating Haar-random unitaries. And at the same time, I'm going to convince you that this PFC ensemble is a secure PRU. So it's going to be actually proof of both of these with a single technical claim. Before I state that claim, let me give a more precise definition of this permutation function Clifford ensemble from this work of Mecker, Premba, Sinha, and Yuen. So P is going to be a unitary that does the following map. It maps every ket x to ket pi of x, where pi is going to be some random permutation on capital N. So capital N is just my abbreviation for 0, 1 to the little n. So it's a random permutation applied in place. F here is going to be a random function, again, applied in the phase. It's actually kind of the same as this O sub little f I was writing before, but keeping with sort of the convention, I'm going to call it capital F now. And finally, this C, it's called C because kind of the standard proposal is a sample C from a Clifford, but really what matters is that C is a random unitary sampled from a unitary 2 design. And a unitary 2 design is just any distribution on n-qubit unitaries that has the property that its second moments match the second moments of a Haar-random unitary. So Clifford is sort of the natural example of such a thing, but really any unitary 2 design works. Okay, so the central technical claim is that this path recording oracle simulates queries to a random PFC. And so what I mean by this is that if you look at 2 different executions, one on the left where you have an algorithm that queries a random choice of PFC, so random permutation, random function, and C sampled from a 2 design. And on the right, you have the state you get after you run the path recording oracle. You implement the queries with PRO, and you trace out the purifying state. And the claim is that for any 2 design D, that the mixed state you get on the left is close in trace distance to the mixed state you get from running this path recording oracle. And I want to emphasize this point here that the reason that this claim is so powerful is that the state on the left, this mixture over P, F, and C, that mixture has explicit dependence on the choice of the 2 design. Like it's, I mean, when you change that 2 design, it's going to change what you're averaging over, right? Like you're sampling C from the 2 design. However, this row, there is no reference to any particular 2 design on the right-hand side. That is just queries to this fixed deterministic object, this PRO. So row, it's completely independent of the choice of the 2 design. And really, that's what makes this claim so powerful. This kind of the fact that you're kind of invariant under the choice of the 2 design. That no matter what 2 design you have, they're all, the mixed state you get is always going to be close to this fixed row. And so this is how we use this claim to get all the things we want. So in particular, you can instantiate the 2 design in any way you want. And one choice of a 2 design is literally to use a Haar-random unitary. Trivially, a Haar-random unitary is a 2 design. And if you plug in D being a Haar-random unitary, and you sample C from the Haar measure, then PFC is also going to be a Haar-random unitary. Okay. So this claim, which says that queries to PFC are indistinguishable from queries to the path recording oracle, that immediately tells you that the path recording oracle simulates a Haar-random unitary. And then the other way that you can instantiate this claim, or this 2 design, is to plug in D being a uniformly random Clifford. And in fact, when you do this, you can go ahead and actually make the P and the F efficient as well. You can replace the truly random permutation P and the truly random function F with cryptographically pseudo-random instantiations of this, which are known to exist from prior works of Zandri, assuming one-way functions exist. And so using this, you can get that PRUs exist. In particular, that queries to PFC when C is Clifford are indistinguishable from queries to the path recording oracle, which are indistinguishable from queries to a Haar-random unitary. Okay. So really, playing with the choice of the 2 design is kind of how you get different consequences of this main claim. Okay.
And if you care about efficiency, right? I mean, a random Clifford can be sampled efficiently. There's small description, so forth.
Yes. Oh yeah, I forgot to say that, but yeah, that's what's going on in the second step. That PFC sort of without any further specification is not actually an efficient distribution, efficient ensemble of unitaries, but it can be made efficient. And so that's why you pick a Clifford and pseudorandom P and F. Okay. So next I want to do or sketch at least the proof of this claim. There's really going to be two parts to this proof, and most of the core intuition that I want to convey comes from this first part here. This first part is saying that when you query this path recording oracle, actually it simulates, kind of in the same sense as the previous slide, queries to a random PF without any Clifford or without any 2 design C, for at least a well-behaved class of algorithms. So let me not exactly say what this class of algorithms is, but the point is that there exists some restricted class of algorithms A, such that when you query a random just PF alone without the C, that the resulting mixed state you get over the randomness of P and F is close to the state you get when you query the path recording oracle. And then part 2, we have to use the random seed somewhere. And it turns out that inserting this random seed sort of before every query is going to be the thing that prevents the algorithm from querying on these bad inputs. There's going to be input that the algorithm could query that would allow it to distinguish these two cases. And the point of the random seed is to sort of shield the oracle from the algorithm querying on these bad inputs. So this is kind of the high-level sketch, and I'm going to spend most of my time talking about this part 1. So the idea for how we're going to analyze these algorithms that query a random permutation function is, again, this idea of purification. So the standard way of running an algorithm that queries a random PF is just this picture. You sample a random PF, and then you fix this oracle that maps ket x to the state where you have this phase in front of -1 to the f of x, but also the state has been replaced by ket pi of x. Okay, so this is what the action of this PF map together, applying f followed by a permutation p. And what we're going to do is, instead of thinking about querying such an oracle for a classically random choice of the permutation pi and the function f, I'm going to consider the following purification, where I'm going to have on some register hidden from the algorithm. I'll start that register off in the uniform superposition over every possible permutation pi and every function f. And then I'm going to apply this controlled PF oracle. So all my queries are going to be to this controlled PF, where controlled PF means that I'm applying an oracle that is looking at this register containing pi and f, and it's reading that register to determine which permutation, which function to be applying to the algorithm's register. And so these two are perfectly identical, and the way you can see this is because this purifying register is hidden from the algorithm's view, it's basically measured at the end of this execution. And that measurement commutes with these control operations. So it's the same as if you had measured a random pi and f at the very beginning, and that's precisely the execution on the left. Okay, so these are perfectly identical from the algorithm's point of view. And so from now on, I'm going to switch to this PF purification world. Okay, so in this purification world, all the oracle queries are to this controlled PF oracle. Let me just write this down again. It's mapping ket x, tensor ket pi f. And it's going to map that to -1 to the f of x. It's throwing this phase in front from the function. And then it's mapping the state ket x to ket pi of x. And then it leaves the pi f the same. And in order to say anything further, I want to do a minor cosmetic modification to how I'm writing this data on the right-hand side. It's going to be quite helpful to do the following changes. First, I'm going to take this ket pi of x state, and I'm going to rewrite it in this funny way. Instead of writing it as ket pi of x, I'm going to write it as the superposition over all y of ket y, but times this indicator variable. So this delta variable, delta pi of x equals y. And this delta is going to be 0 at all choices of y except when y is equal to pi of x. So this delta is just this coefficient that is enforcing that y is equal to pi of x. Okay. So these are just trivially the same. And so of course I can rewrite this state by plugging in ket pi of x as this sum over y and having this funny delta thing. And then what I'm going to do is, let me just rearrange the coefficients. It's going to be sort of a lot more suggestive to move these coefficients, this -1 to the f of x and this delta pi of x equals y, and sort of move it to kind of appear on the purifying register. I mean, they're just constants that are multiplying the expression. I can write them wherever I want. And so I'm going to write them right next to the ket pi f. Okay. And so let me use this expression from now on. And so this is what a controlled PF query is doing. So far, like basically nothing has happened. I've just rewritten like what a query does. And now let me remind you that I want to relate these controlled PF queries to these queries to this path recording oracle PRO. And PRO has this definition, right? It's mapping ket xr to the superposition over y's of y tensor R union xy. And I want you to have the following intuition for what this path recording oracle is doing. It's creating the superposition over like nearly all the y's, and simultaneously, like, you know, when it turns this x into a y, it's simultaneously recording the ordered pair xy in the purification. And so what we're going to show is that this controlled PF oracle is doing almost the same thing. And it's not yet obvious yet, like just from the way it's written down. But what I'll show you is that there's actually a different way to view this controlled PF oracle that will make the connection a lot more clear. So remember that when you make these queries to the controlled PF oracle, the initial state of the purifying register begins as the uniform superposition over all permutations pi and all functions f. Like before any queries, you start with that state. Okay, so then what happens after you make one query to the controlled PF oracle? Well, something's going to happen to the adversary's register. It's going to go from some x's to some y's, right? But when you go from any particular x to any particular y on the adversary register, on the purifying register, you're going to get the corresponding state, like that's the uniform superposition, but it's picked up these coefficients. It's picked up a -1 to the f of x, and it's picked up this delta pi of x equals y. Right, so that's the effect of what a query is doing. You should think of the query as mapping the x on the adversary register to the superposition over y, and at the same time, like multiplying on these coefficients onto the purifying register. So you've picked up one coefficient after one query, but after t queries, your purifying register is going to be a superposition of these states that are like that seem like uniform superpositions over pi and f, but they've picked up t of these coefficients, in particular t of these -1 to the f of xi's and t of these delta pi of xi equals yi state, like coefficients. And so let me just give these states a name. Let me call them pf sub r, and r is just my shorthand for this set of ordered pairs xi, yi. And if you kind of look at the way this definition works, it's you know, only this set of ordered pairs matters. Like it doesn't matter like the relative orderings of the xi, yi's, particular like this -1 to the f of xi, like it doesn't matter the order of the x1 through xt's are. It's invariant under the order. And same with these deltas. Like it's really because you're just multiplying in these coefficients, which is why the only the set of these ordered pairs matters. Okay. And the point is that these PFR states are kind of the right basis in which to understand what controlled PF is doing to these overall states. In particular, if you look at controlled PF and the way it acts on X tensor PFR, so instead of thinking of it in the normal basis of pi and f, I'm looking at it in the PFR basis, then what it does to X tensor PFR is it maps it to a superposition over Y tensor, the state you would have if you added xy to the set. Right, intuitively remember like what controlled PF is doing is it's throwing in like one more like -1 coefficient, one more of these yellow coefficients, and one more of these pink coefficients, right? And looking at the definition of PFR, that corresponds to introducing one more ordered pair into the set. So that's what controlled PF is doing. And now if you look at PRO, like, they're like almost identical, right? PRO is doing the same thing, but sort of directly on these ket R states. And so the only thing that's left is that you actually want these PFR states. You want to be able to say that these PFR states behave like these ket R states. And it turns out that is true for most of them. So these PFR states are actually orthogonal to each other, all orthogonal, if you restrict the set of R's where all the X's are distinct from each other. So in particular, what this is saying is that ket R, like just looking at that set of ordered pairs, it's kind of like a compressed representation of this PFR state. Like PFR, by definition, it's like this exponentially many qubit long state, right? It has the entire description of a random permutation or a permutation pi and a function f. These are exponentially large. And it's saying that you can really compress this representation down to just the set of ordered pairs, at least when the x's are distinct. And so putting all this together, what this is saying is that the following two executions are perfectly equivalent from the algorithm's point of view. The one on the left being the algorithm queries this truly like this purification of PF, and the one on the right where it queries this path recording oracle, because these PFRs are really just these ket R states up to relabeling. And that register is being traced out from the algorithm's point of view anyway. So these are perfectly equivalent, except for one thing, except if you have these states R that has collisions in the xi's. Okay. So I lied a little bit. They're not actually equivalent. The algorithm can definitely tell the difference. But as long as the algorithm doesn't query on these states, they would actually be the same. And so that's where the two design comes in. So let me kind of gloss over this part. But the claim here, and like what we show in the paper, is that inserting a random C sample from any two design before every query is preventing the algorithm from querying on these sort of collision states. Yeah,
Can I ask a question though? So if I think of a two design as sort of like a pairwise independent permutation, let's say, and it's sort of like a classical intuition, right? So it's certainly the case that if I make T queries, well, pairwise independent function, let's say, right? The chance that there's a collision is T squared over whatever, the right number, right? But here you're making these queries adaptively.
Yes.
So maybe that's still true.
Yeah,
That's
so there's
probably
actually
still true.
good. So kind of like how are we handling the adaptivity? And unfortunately, it's like not something that I've really built the slides for. But it's this purple box here where I'm saying inserting the two design prevents these collisions. I'm hiding there I think kind of the nicest part of the proof really, which is sort of how the purification allows you to think about adaptivity. And so I want to remark, like this property of two designs that it prevents collisions, like that we took that straight from the prior work of Mecker, Prembus, and Yuen. But in that work, I mean, you're restricted to these algorithms that are making these parallel queries, and you can talk very explicitly about like what is this distinct subspace, these like subspace of states where they're all pairwise, distinct.
Right.
Kind of that subspace doesn't exist anymore in the adaptive query world, right? You can have these queries that are applied on top of each other, right? Like applied in sequence. So how do you talk about any such subspace, right? Of like distinct states. And that's where the purification is sort of nice, because actually the purification allows you to talk about that subspace because it appears on the purifying side. So that's what actually happens in the proof. Like it kind of, by looking at the purification, you can look at these registers where you literally have the query kind of written out. Like, I mean, R is storing x1, y1, x2, y2, like sort of explicitly. And so you can actually talk about the distinct subspace on the purifying side. And that's kind of the secret sauce for like how you handle adaptivity with purification.
Fermi, is one way of thinking about that is that the purifying register in some sense doesn't care about the order in which the different X's come in. Somehow it just mods up by that.
That's certainly true. I'm not sure if that's like the reason why like the argument's able to that we're able to make the argument go through. It might be, yeah. I'm not sure.
Is the argument eventually just that T squared is just the sum of J from 1 to T? So since you have explicitly on the purifying register that there are only T targets, the next one has only that many to hit. Is that what you...
Yes, yeah, it's true. It's just that sort of making that argument rigorous requires you to talk about, the probability of your state landing in a certain good subspace. And the insight really is that it's much easier to formulate such a claim, like mathematically, when you have these purified states. Like talking about states in the good subspace when like you don't actually have a subspace, like the notion of distinctness is sort of spread across different queries. It's much harder. By the way, we started at 10:05 and I have a few minutes left, so maybe let me just try to wrap up. So just to recap, like what this proof was doing, I mean, we defined this path according oracle object, and then using purification, we showed that this path according oracle simulates queries to a random PFC for any two design that C is sampled from. And this is how you get the main simulation result and the existence of PRUs. And so beyond the PRU application, I think more generally, this path recording oracle just gives you a new tool for proving theorems about random unitaries. And so just a very quick example, like one application that I particularly like is that it gives you a new way to prove this very powerful gluing lemma introduced in a recent work of Schuster, oh, the citation is wrong, it should be SHH, Schuster, Haferkamp, and Huang. This is kind of the key lemma that allows you to sort of generically take any like random circuit of a certain depth and sort of compress it down to having much lower depth. It boils down to proving this gluing lemma. And what the gluing lemma says is that if you have two Haar-random unitaries, U1 or U2, and they're applied in different systems, but they overlap on some number of qubits. So U1 is applied on systems BC, U2 is on systems AB, and they overlap on some super logarithmic number of qubits. Then the claim is that you can't distinguish this from a single Haar-random unitary on the overall system. Like if you have a button, and every time you press the button, it either applies U1, U2, or it applies U3, Haar-random U3, you can't distinguish these two. And so this is proven in his work of SHH using, it's not a terribly complicated proof, but does use the machinery of the Weingarten calculus. And if you want a completely elementary proof of the gluing lemma, you can get this like very simple proof using this path recording oracle framework. In particular, you use the fact that every time you have a Haar-random unitary, you can just replace it with this simulation object. So you take U1, replace it with the path recording oracle. You take U2, you replace it with like an independent instantiation of the path recording oracle. You take U3 and you replace it with yet another one. Like all of these steps, I mean, that's like, we're allowed to do this by the main theorem of this paper. And now in the path recording oracle view, all you have to prove is kind of a statement about like bounding distances between quantum states. In particular, you just need to show that like morally or from the algorithm's point of view, when you have these two different oracles that are recording two different sets, there is a way to kind of stitch together these sets to show that the action of these two like PRO1 and PRO2 from the algorithm's point of view is basically the same as like one larger path recording oracle applied to the whole system. Okay. So there's a little bit more to it, but you really just have to construct an isometry that maps one purification to something very close to the other purification. And so more generally, I think anytime you have a statement now about random unitaries, you want to understand it, I think it's a good starting point to just, instead of applying the standard like Weingarten toolkit, at least seeing if the path recording oracle can give you maybe like a more direct proof. Okay. One last thing I want to say before I wrap up is that I mentioned that we have this result on queries to the inverse as well. And in the paper, we give this different path recording oracle, like a sort of symmetrized version that allows you to simulate both forward and inverse queries to a Haar-random unitary. And using this, we get pseudorandom unitaries secure against both forward and inverse queries. And so this is kind of, the simulation is sort of exactly the thing you would expect, that now if you have access to PRO and PRO dagger, again, for like a slightly different definition of PRO than the one I showed today, then you get a state that is close to the state you get when you have access to U and U inverse. And this actually is, I'd say like an order of magnitude more challenging than the forward proof. It was quite difficult actually to get all the parts to come together. And really the conceptual difficulty of handling the inverse case is that like the way I define this path recording oracle, it's always adding ordered pairs to this set. Like it's only recording paths. But when you have inverses, you also need to have some mechanism to erase, right? If I do U and U inverse, I should be exactly back to my original state. I shouldn't have any entanglement with the purifying register. So I need to have some mechanism that like knows when it's time to erase something from the set. And that's what really is like the technical challenge of understanding the inverse case. And so you'll have to see the paper for the details on that one. So let me just end with a few future directions. So I think there's a bunch of discussion about like maybe physics applications of pseudorandom unitaries. Maybe they're a useful object for modeling like black hole dynamics, chaotic systems. I just want to ask more broadly, like, do we have the right notions of pseudorandomness? Like, for instance, is there a case to be made that the inverse secure access is actually the notion you want, or something else entirely? I don't know. Another maybe physics-related question is whether there is some physical interpretation of this path recording oracle. And the reason I ask this is that it turns out that the way that we define this oracle, where you're always adding these ordered pairs to these sets, these are like precisely the same operators you have in quantum field theory when you look at these like bosonic creation or annihilation operators. And so the fact that they're like exactly the same makes it reasonable to wonder, like, is the path recording oracle, like, does it correspond to some sort of physical process? It'd be very interesting if there's like some physical process that simulates Haar-random unitaries. I think it'd be interesting to explore whether this PRO view has any consequences for random matrix theory or representation theory. More broadly for quantum computing, I think it seems quite promising direction to use this path recording oracle to just study quantum algorithms more generally. And finally, cryptographers think there's quite a lot to do with PRUs. Like I think, have a lot more room for finding further cryptographic applications. And I think there's a particularly exciting direction of building cryptography from assumptions weaker than one-way functions. And it's entirely plausible that we could have pseudorandom unitaries without one-way functions. And I think in this direction, like, basically nothing is known. So I think I want to wrap up there. Thanks a lot for your attention.
Great, thanks. That was a beautiful talk. Any questions before we move to the panel? So if you stop sharing the slides, maybe we can pin the...
There are a couple of questions in the Q&A, maybe.
let's see.
Yeah, Fermi, do you have access to the Q&A? Do you want me to read it for you?
Yeah.
In particular, the second and
More about simulating. Sorry, so there was a question from the question about, can you say more about simulating random permutations or other distributions over classical oracles? Xandri's original framework makes it hard to handle non-IID distributions. What types of distributions can your path recording oracle handle? Good question. Okay, taking the question at face value, it only really handles one distribution. It handles Haar-random unitaries. But maybe I'm missing the...
But actually it does more, right? I mean, it handles PF unitaries as well. Modulo
it doesn't quite handle them, right?
Yeah,
yeah, I think the only like yeah, it only handles like actual Haar-random unitaries or any distribution of
PFC,
unitary
right?
or matrices that are
it handles all PFC, doesn't it?
Yeah.
Oh, good. I completely, yeah. Sorry. No, you're totally right. Yeah. So let me take back like the entire last minute of me talking. It does handle many other distributions. And I guess I think it's still an open question to figure out like what other distributions you can handle, right? There's potentially many other constructions of pseudorandom unitaries. And I guess the point here is that, you know, you could have two different distributions of matrices that are completely different, but maybe the difference cannot be detected by any quantum algorithm, right? And that's really what this whole proof is about. We don't have any explicit characterization of like what are all the different distributions, though. I mean, it would be nice to have that, but I think that's like quite far from what we currently have. Thanks so much. How is the notion of inverse path recording achieved? Let me punt on that question. yeah, lots of suffering. So, what is cap? Yeah. Okay, I see.
Great. So shall we move on to the panel? Is it possible to pin the? Okay, great. So we have a great panel here. Vinod, of course, is one of my favorite cryptographers who's moved over to the dark side. He's been doing more quantum than most. So Vinod, welcome. And Henry, so Vinod's at MIT, of course. Henry at Columbia. Henry is he's done a lot of work on infinite randomness expansion, MIP star equal to RE, and then of course many things that are relevant to today's talk, the PFC proposal itself, and Douglas Stanford from Stanford University, and Douglas is a physicist. He does quantum gravity, quantum field theory, string theory, and great to have you, Douglas. I think there should be a very interesting discussion about the physics implications of Fermi's talk. So maybe I'll leave the floor to you, to the panelists, to speak in any order you like about what your thoughts on the talk. Maybe in the order, Vinod, do you want to start? And we can move in there.
Fantastic talk and really, really, really nice result. So I guess let me start by sort of bringing up sort of two classical transformations, right? One from non-adaptive PRPs to adaptive PRPs. This is Berman-Heitner from about a decade ago. And what they do is they take a non-adaptive PRP.
Sorry, PRPs are pseudorandom permutations?
Pseudorandom permutations, I'm sorry.
Yeah.
Can't help the acronyms. Pseudorandom permutations, right? Which are, on the one hand, non-adaptive secure. You want to turn them into adaptively secure, sort of like what Henry et al. Did to what you guys did, right? And the way the transformation works is remarkably simple. You compose the pseudorandom permutation with a pairwise independent function. So you take a non-adaptive pseudorandom permutation, compose it with a pairwise independent function. There's a proof that you get an adaptive pseudorandom permutation. And if I think about random Clifford as sort of doing the job of a pairwise independent permutation, feels that there is a sort of a connection here. So that's one transformation that comes to mind from the classical world. The other one is a transformation from pseudorandom permutations secure against forward queries into ones that are secure against both forward and backward queries. And the way it works is you take I believe this, I have to sort of go back and check myself, take a pseudorandom permutation and compose it with its own inverse. And maybe there's a pairwise independent hash that needs to be applied on both sides, perhaps. So in any case, there's a generic transformation from pseudorandom permutations to strong pseudorandom permutations, which is, forward versus forward plus backward queries. I wonder if, at least in your case, right? You're saying the strong version of the claim actually requires significantly more work to prove. I wonder if there is something, if there's intuition that one can draw from the classical world to come up with a simpler proof. That's sort of one thought. I guess sort of the obvious.
Sorry, Vinod, before we move on, can you say a couple of more words about to go from forward to forward and backward? What do you do? You take the
What do you do? You take, I believe it's essentially this, but I might be lying a little bit. So you take a permutation and you compose it with the inverse of the permutation. And that is sort of what is happening here, right? So in the construction, you take PFC and you compose it with sort of like the inverse, which is C inverse, which is C. Inverse of a random Clifford should be a random Clifford, times F inverse should be a random F, times P inverse. So something simpler than that is actually happening in the actual construction.
Two separate instantiations, right? Not
the
same one.
Two separate instantiations. Yeah, two independent instantiations, right? Your construction is slightly simpler because you.
Oh no, I think that what you're describing would be exactly the same.
Is that right?
I think that you take two PFs and you multiply them,
okay,
you will
so
get literally another PF.
so maybe there's a two Fs in my construction and one F in your construction.
Yeah.
Some slight difference.
Yeah. Okay. Oh, sorry. There's actually one thing that I lied a little bit in the talk. For the forward proof, the F can be binary or above. Like, so when I talk about random functions, it's like random binary phase, ternary phase, or higher, Q-ary phase.
Yep.
And the PFC, the forward proof, it works for any like Q-ary phase for Q like 2 and bigger. But for the inverse proof, we don't know how to do it for Q equals 2. Like, actually, we only know how to do it when Q starts being 3. So we only like know how to have like ternary phase or higher. Yeah, I don't know. It's a mystery there, but also
in one case
a
you have
barrier for the. So Vinod, I think maybe your video is acting up, or I'm not sure if it's me, but
I think yeah, not sure. Yeah, well, one of us, but in any case, so the difference I can see between 2 and 3 is real faces versus complex faces. Is that what's happening in the?
Okay, I think the
Sorry,
audio
this is
is a little
probably me.
choppy, but yeah, let me just try to answer what I think the question might have been. Is kind of like why ternary phase or higher. And yeah, it's basically what Vinod was saying, that when you have ternary phase or higher, you can actually distinguish between forward queries and backwards queries. Like a forward query gives you like a first root of unity, a backwards query gives you a second root of unity. And those in the purification can be like distinguished from each other. And that is quite important. Like, turns out you have to sort of record the forward path separately from the inverse paths, like the paths through the inverse queries.
But
yeah,
it
so
could be
I answered your
that
question when you weren't here, but
but it could be that the binary phase construction could still be inverse secure, right?
it
or do
could be. If I had to bet, I feel like it's not, but we haven't been able to come up with that attack. Yeah.
Yeah, so I guess just to summarize, there are sort of, seems to me, classical analogs to these constructions, and it'd be good to understand a bit more what is exactly the analogy.
Yeah. By the way, Umesh, with the format of this thing, should I respond after all the? Umesh, I think you're muted.
Sorry, you should respond whenever you like. Yeah, you should respond immediately if you like.
Yeah, no, I think so. I think it's a really interesting proposal that maybe there are. I honestly just wasn't aware that this was a thing that people had done. Yeah, neither Robert nor I are all that familiar with the pseudorandom permutations literature. And yeah, I think it's quite plausible that that one can prove kind of generic like boosting theorems that like boost a sort of weak security notion to a stronger one. And just, I mean, looking at the way that this C-PFC construction looks, it's, I mean, seems quite plausible that something like this is true. Yeah, and I mean, we do, like with this gluing lemma, that's like one example of some kind of composition theorem, like a very different one. But yeah, I think it's totally within the realm of possibility.
That's right. That's right. Okay, cool. So if I may, let me point out one more thing, which I thought was, I didn't know about this before. So there's a theorem that says pseudorandom unitaries need to have complex faces, right? I mean, if I remember correctly. So your construction says that any two design needs to have complex faces in particular. Because if it didn't, you would have a PRU with right. The PFC construction implies that.
You don't even need my construction to say that, though. Also, not my construction, but you know, the same proof that says that PRUs need complex phases also applies to two designs.
Also applies. Yeah.
The proof is to I think apply U to both sides of a maximally entangled state. And kind of you get this nice cancellation if U is real. And that doesn't happen if U is
Got it. Cool. Thanks.
Great. Thanks, Vinod. So, Henry, would you?
Yeah. So yeah, thanks for the talk for me. That was a really fantastic talk and fantastic work. Yeah, maybe I'll just share a few reactions that I have. One is that, yeah, I think one thing I'm very, very happy about, yeah, I guess we came in March, or we chatted in March, and then, at that time, I mean, that wasn't so long ago, but it was sort of just seeming like, there's some proposed constructions for PRUs, and it was kind of unclear how to show, all these security notions. And then things developed really quickly. And I think the thing that I'm really happy about is that this path recording framework that you guys found is really, I mean, it's really nice and really, and above all, like really user friendly. Because, I remember that when Makran, Tony, and Alex and I started thinking about the PFC construction, we found it quite intimidating to analyze because it seemed like the only way to properly analyze it was to open up all these yellow books and on representation theory, and that sort of seemed like it's really only accessible to kind of like this small community of people who really know this stuff. I mean, we eventually did open those yellow books and we learned the bit of representation theory that we needed, which I'm glad I did. But I think ultimately, like this path recording framework is somehow, it's just very natural from a quantum information point of view. You sort of just do like the natural thing, like you go to the church of the larger Hilbert space and view everything as a pure state and just kind of follow your nose. So that part is really, really nice. I have like a zillion questions, but maybe I'll talk about the ones that are less well thought out, less concrete. So one is that, yeah, a couple people brought this up, but I'm kind of curious whether like what your technique says about the random permutations, like analyzing oracle access to random permutations. And I mean, I don't know too much about this area, but apparently I think it's been a open problem for a while to extend Zandri's recording technique to random permutations. And I'm wondering, I mean, you didn't really talk about your inverse proof, but do the techniques there of like keeping track of recording and erasing queries, could that possibly tell you how to analyze random permutations or?
Yeah, that's a really good question. Robert and I have wondered this, and yeah, I want to say maybe I should give a little bit more intuition than for the inverse proof. Like what the inverse proof is doing, or like what the inverse path recording oracle looks like. It's kind of funny, like you have access to now two oracles, an oracle for U and an oracle for U inverse, and actually, like if the way the path recording oracle in that case ends up coming out, basically says that most of the time, like when U and U inverse don't interact with each other, they're actually just like two independent Haar-random unitaries. It's kind of curious, I guess, like in hindsight, maybe not that surprising. And it kind of, they always behave that way, except when you just kind of stack two on top of each other and you have one cancel out a previous one. And in that case, then they actually cancel out. And that's kind of the way that this inverse like path recording oracle works. It's that actually it just has two different sets. And it works almost as if you were just independently instantiating two random unitaries, except it has this one extra branch, like it has this like sort of if statement. And that if statement is like looking for the case in which two unitaries are canceling out. And it uses that to say, well, actually, now I want to kind of cancel out a previous operation rather than treat this as a new instantiation of like the second object or a new application of the second object. I want to just get a little bit of context there for kind of how the inverse proof works. And then I guess there's this question that you asked of, like, can you apply that intuition to sort of stitch together two permutations, right? Like a permutation and inverse. Like maybe you can stitch together, maybe you can treat a permutation and access to the inverse as two separate objects, except on like the one branch where they cancel each other out. So it's plausible to me. We haven't actually figured out how to make this work. But I do want to Asley, I think that I thought this question was recently solved, or that there is at least a preprint that kind of I think I want to say by like maybe Julia Volta, Michael Walter, and a few others that kind of the trick was using a new kind of or a particular kind of representation of random permutations that sort of allows you to kind of recover some of like the independence. It's like decompose the permutation to like transpositions or something. So I'm not totally familiar with how that works, but I think it's not open source anymore. I'm not sure. Yeah. It's certainly though like a reasonable thing to try. Like, yeah, does it say anything about random permutations? We don't know.
Yeah, I guess I didn't know about this paper. But then I guess sort of a follow-up thing that I was thinking of was, is there I think it'd be really cool if there was some kind of more unified perspective on all these different recording techniques and path recording techniques that somehow, I mean, on one end, we have a recording technique for random functions, maybe now random permutations, which are very it's completely classical. But then, on the other end, we have now recording technique for fully random unitaries, Haar-random unitaries, which are, highly non-classical. So is there some way of, what's in between? Is there something in between?
Yeah, that's a great question. Maybe kind of a partial answer, or maybe let's say a low confidence answer. My feeling is that path recording is maybe the most general way to, or is general enough to kind of encompass all of the previous, all of the other oracles, in the sense that when we call it path recording, we're referring to recording the Feynman path. Like if you take the sort of path that the algorithm state takes through all the oracle queries, like through oracle query 1, it goes from x1 to y1, next query x2 to y2, and so on. Like where this oracle is like recording the path. But then, and I think like at that level of generality, I think all of the oracles are doing something like this. It is just that when you query, say, like a random function, you don't actually traverse through all possible Feynman paths. Whereas when you're querying a random unitary, you actually do some basically over all the different paths. It's just that like when you have a random function and you're like, say, applying it in the phase, you don't go from x to any y. You go from x to x and you just pick up a phase. And then that x actually gets recorded. So I think that like, or I have this feeling that maybe like this notion that the oracles are recording Feynman paths is fairly general. But yeah, it would be really nice to make that precise. And I have no clue what's going on with permutations.
Cool. Yeah, maybe I can circle back to my other questions, but yeah, after Douglas.
Okay, I have two things. Let me first share my screen. So in physics and in quantum gravity, we've been interested in some ensembles of random matrices. And one of the things people study there are the statistics of eigenvalues. So I was kind of curious about the statistics of eigenvalues in this PFC ensemble. So oh my goodness. Do you see this?
Oh yeah.
Okay, so I did this calculation. Well, I don't know completely if it's right because I got ChatGPT's help to do this calculation. And so what I'm plotting here is the statistics of the eigenvalue spacing distribution for different ensembles of unitaries. So you take a unitary matrix, you diagonalize it. All of its eigenvalues are phases. They live on the unit circle. You write down the list of their angles to make them into real numbers instead of complex phases. And then you order them and compute the differences between the nearest neighbors. And then you plot the probability distribution for that difference. So typically the average difference between the eigenvalues is like 1 over the number of eigenvalues, or 2 pi divided by the number of eigenvalues. So here's 3 different ensembles of random unitaries. The top left is the P, random permutation, and this is the top right is F, and the bottom one is C. And the orange curve is the distribution that you would get if it was a random unitary. So these are all pretty different from that. Then at the other end, if we look at PFC, then it looks kind of the same, which is interesting that like as far as I know, there's no direct argument that the eigenvalue statistics, or at least the nearest neighbor eigenvalue statistics for these ensembles has to match that of Haar in order for it to be computationally distinguishable from Haar. But it looks like it does. Something I'm sort of surprised by is that if we look at the other thing where you take 2 out of the 3, then in 2 of the cases, it still looks sort of like the Haar distribution, like PC and FC. So as long as there is a C there, the spacing distribution sort of looks similar to this. But for PF, it's very different. It looks a lot like the distribution just for P. So I'm curious, do you know for PC and FC, do you know those are not PRUs?
Oh, I'm pretty sure that they're not. Like, yeah,
So you're conjecturing that they're not PRUs, but the eigenvalue statistics are not enough to distinguish them from random. That's plausible, right?
I mean, that could certainly be the case. We could take some very simple matrix and just, if I could take a computational basis matrix and just diagonal the computation basis and put like just the eigenvalues of a random unitary matrix, then we'll have the eigenvalue statistics of a Haar-random matrix, but it will be very different.
Right.
It's interesting because eigenvalue statistics are, even if they were different, I don't think they would be an efficient distinguisher.
Right. Yeah. But the reason I was interested in this is it's like we care about this thing, these eigenvalue statistics, and you guys don't. You care about this notion of computational distinguishability.
Sorry, Douglas, can you say why you care about these?
One of the reasons we care about them is because they can be computed in quantum gravity by various types of wormholes. So, well, okay, let me say more broadly, there's an old reason people care about them, which is this Wigner idea that if you take a sufficiently complicated Hamiltonian, then its eigenvalues have the statistics of a random matrix. And so it's been used for decades as like a diagnostic of chaos. Diagnostic of quantum chaos is eigenvalue statistics look like that of a random matrix. And in recent years, people have got good at computing that kind of thing using holography. And we understand now sort of random matrix eigenvalue statistics as arising from space-time wormholes. So it's kind of important that the eigenvalues of the Hamiltonian of a holographic quantum system should have random matrix eigenvalue statistics.
But can I say something about the comment before? So there's no computational indistinguishability here, really, right? I mean, it's really like trace distance or like like diamond norm or whatever indistinguishability.
Well, that's a type of computational indistinguishability, I think, because it's approximate trace. I mean, it's not exact.
But okay, I guess it's a question of terminology, right? I mean, to me, computational indistinguishability sort of means that the algorithms trying to distinguish one thing versus another are polynomial time bounded. There is no such thing in Fermi's result, really, right?
Yes, it's okay. Maybe we should say practically indistinguishable, even with unbounded computational resources.
Right.
One other comment I wanted to make, just based on the discussion you were having with Henry, Fermi, is that it seems like there should be a path recording oracle thing that's efficient for any group, like including permutations or unitary, like even an exact version of the unitary group, just like using this idea that we discussed a bit with Jeff Pennington and the Stanford workshop. It seems like that works. Like you just need to be able to efficiently do representation theory. Like the oracle part needs to be able to efficiently do representation theory.
Douglas, could you say this a little more?
Well, so Fermi mentioned that there's a way of thinking about an ideal path recording oracle, or an ideal oracle as being like a controlled U operation. So you have some auxiliary system that has a superposition of all U's, and then you act on your system with the controlled U operation. And the idea that Jeff Pennington explained is that you can think about that as a simple state, like in a different basis. So I think Fermi mentioned that in Xandri's result, it's useful to think about the Fourier basis. And the analog of the Fourier basis for an arbitrary group would be like the basis of functions on the group that are given by representations. And if we think about it in that basis, the original state, which is just the integral du of ket u, is just the singlet state. So that has a very simple representation in this basis. And what happens when you act with the controlled u operation is that you take whatever representation you had previously and you tensor in the fundamental representation. So if you act with this like k times, then the representations are not too big. They're just like k copies of the fundamental representation. And so you need to be able to do representation theory, which means you need to be able to decompose tensor products of representations into irreducible representations. You need to be able to do that for like, k copies of the fundamental, which I imagine is an efficient procedure for, I don't know about any group, but it seems plausible. So that would work for the permutation group or for the Haar group, whatever thing you can do with representation theory efficiently for.
So, and what you're referring to as the fundamental representation, what do you mean by that?
Yeah, so I should have brought like an iPad or something so I could draw. So let me yeah, how do I draw something? Better not try to draw it with my mouse. Let me describe the Hilbert space of the oracle would be the Hilbert space of functions on the unitary group. And we would describe it in the basis corresponding to representation matrices. So the representation matrix is a function on the group, and that's a basis for this Hilbert space. So to begin with, we start with the singlet state in that oracle system. And now we need to ask what happens if we act with the controlled u operation. So we have some additional state, let's call it psi, and we have our singlet state. And we want to act on this with a controlled u operation. And the result of that will be the following state. It will be a function on the group, which is the fundamental representation with so that's a representation matrix. I mean, to say the bra and the ket. The bra and the ket are the initial state and the final state. It's Fermi's x and y. So instead of a pair, x comma y, we'll have the x and y matrix element of u in the fundamental representation. And so that will be the oracle state after one iteration. The oracle state after k iterations will be k of those things. It will be x1, u, y1, x2, u, y2, x3, u, y3, and so on. So it will be k copies of the fundamental representation. And the efficient way to handle the quantum mechanics of that thing will be to decompose that k-fold copy of the fundamental representation into irreducible representations.
So something like this should be already happening in the oracle state, right? And what Fermi was describing.
I think Fermi's version is it's an approximate version of this. Maybe if we think about it, we can think about it as some kind of approximation to the representation theory problem you have to do. But it seems like it should be efficient to do it exactly for any group. Unless there's something really hard about the representation theory.
Yeah, so do we know how to do to decompose into irreps for an arbitrary group efficiently?
I don't know.
Doesn't that require? Yeah.
for this, we might need to look in some of the yellow books that Henry was referring to.
or beyond, maybe.
Yeah, during this talk, I was actually just Google searching for representation theory for Yuen, and I don't know.
Yeah. I mean, we know how to do it for SN, etc., right? But whether we can do it in general is a different question.
So on that note, I was wondering that, I think Fermi, you were alluding to this, like could somehow this path recording thing, you sort of proceed, like for a quantum information person, you sort of just proceed like, you follow your nose, you have the purification and so on, and you think about this compression. But somehow this, like once you compress the oracle register, like in some sense, it's kind of discovering like the right basis to like understand the mixed state on the algorithm side. And but on the other hand, like from the representation theory point of view, like what basis to look in, like use the sure-while basis, right? Like that's what all the yellow books tell you. And then like all the, it seems like the hard part was to kind of like rewrite the matrix in terms of the sure basis and then, understand the dimensions of all the irreps and so on. But like in your technique, it somehow just kind of seemed, I don't know, do you have a sense in which it kind of like naturally finds this irreps, or like does it do that, or is it somehow just avoiding it altogether? Or I don't know, this is very vague, but
Yeah, great question. Let me start out with a disclaimer that I don't know any representation theory at all. So I probably can't like answer that question very precisely, but
That's a plus.
I mean, we certainly weren't like intentionally like guided by any like search for irreps here. This may or may not be relevant to what you just said, but something that is interesting about kind of how you find this path recording oracle is that at least if you don't know any representation theory, if you write U in sort of the naive basis of just like the matrix description of U, it is like entirely unclear what to do once you write down the purification. Like you'll have these states that have like weird orthogonality relations with each other, and when you try to like compute like how these like purification states are related to other purification states, you're gonna just recover the Weingarten coefficients. And probably like the trick to thinking about it more clearly through the purification view is to not write down a Haar-random U, but to like rewrite a Haar-random U by like pulling out a random P and F. Like the random PF is it kind of like corresponds to like the easy to analyze part of the purification. In the same way that it turns out to be much easier to analyze like a random F with like Marx compressed oracles. And sort of the combination of a random PF also has like a very nice view in the purification picture. And we're like using the like left invariance of Haar-random unitaries to sort of like pull out a random PF out of thin air, show that this kind of already does like most of the legwork of like how a Haar-random unitary scrambles states. And then you only need to rely on like the two design property of the unitary to kind of tie everything back together and like bound the error, I guess. So yeah, that's kind of like I think like the key step in coming up with a path recording oracle, at least if you are okay with having an oracle that has some error, it's like realizing that you can pull out this PF. It's like a weird coincidence that like the only way I know how to derive this approximate oracle, at least through entirely elementary techniques, like just goes through constructing a PRU on the way. Like there's no reason a priori that these two problems would be related. Like how do you simulate a Haar-random unitary and how you construct a PRU? And yet like the nice way to think about a random unitary is to basically conjure up like a PRU construction. In hindsight, that is what happened. So I know we've drifted a little bit from the like initial representation theory question, but yeah, back to that. I mean, I think everything Douglas is saying is sounds totally plausible. And it would be nice to check it with what that work I mentioned about pseudorandom permutations is doing. I think that perhaps like what they're doing is finding some nice representation of permutations. But there should also be a bunch of other applications that haven't been done before, like at least random orthogonal matrices. Like nobody's written down a way to simulate those yet. And maybe what Douglas is saying is just like a general, like, all-purpose way to get exact simulators for all these objects.
Well, it was really Jeff Pennington who suggested this at the Stanford workshop.
Yeah.
Right.
Is your approximate oracle, do you know if that is exact for some other ensemble of unitaries?
That's a great question. Not that I know of.
Yeah.
There is, I think so this isn't written down, and so take this with a grain of salt. But yeah, there is one oracle that you could write down that has that is like the exact purification of like a very nice object. Particular, like in the path recording oracle, there is this condition in the sum where I don't sum over y's that have appeared before in the set. But you can imagine like what happens if you write down an oracle where you do sum over the y's that appear in the set. And now you just have multi-sets, right? And it turns out if you write down that oracle where you include the y's and you allow for multi-sets, and you very slightly change the overall normalization, you actually get an exact purification of what an algorithm sees when it queries a matrix of IID complex Gaussians, sort of with an overall 1 over square root capital N in front. So that when you query such an, like what I mean by query is you literally apply that matrix, right? It's like not a physical operation. That is not actually going to be a unitary matrix, but it is like mathematically well-defined. You know, it's not norm preserving or anything, but neither is this purification. Like I've broken the thing that we needed to get the isometry property. So I don't know, that's like a mathematical curiosity. But beyond this, I don't know of like any other settings where we like have something that like exactly corresponds to.
Yeah, I guess if you query yours many, many times, it starts to do something weird, right? Like it just gives, what does it give?
If you query what many times?
Because y is, if you do it many times.
Oh, the original path recording oracle.
Yeah.
Yeah, it starts getting pretty weird. Like it'll definitely break by about square root capital N or something.
And what happens if you, what happens when it breaks? I
didn't even define it past some point. I think at some point the oracle just it's the zero operator. When there's no more y's to add, for instance, it just zeroes out the state or something. So it degenerates at these large t's.
Right, this mathematical curiosity you just mentioned is really interesting because I'm wondering, like, could a way to sort of another way to look at the eigenvalues of these like IID Gaussian matrices is imagine just running phase estimation with these non-unitary things. I mean, since it's exact, you could in principle just run the phase estimation to like super high precision. This is just totally like wild speculation, but I'm wondering if
that is a very bizarre, but I don't see anything wrong with that proposal. Yeah.
Could you somehow extract information about the eigenvalues of random Gaussian matrices in like a more, I don't know, easy way?
Yeah. I should say, by the way, like the only way that I know how to prove this claim about the thing I just said, that this oracle with this like multi-set version of the path recording oracle simulates queries to IID Gaussians is by looking up theorems about the moments of IID Gaussians. Like I don't actually know how to derive this sort of from first principles.
Interesting.
So, you know, it's totally possible that you could do what you're saying, and then maybe it doesn't tell you anything new. Maybe it only tells you stuff that we like already knew about like how these statistics relate to moments. But yeah, in general, I think this whole question about eigenvalue statistics is very mysterious. I do wonder, like, yeah, to what extent matching eigenvalue statistics is like entirely coincidental or like point at something more foundational. Like the fact that it works for FC and PC sort of makes me wonder, like,
Yeah, I don't know whether I don't promise that the eigenvalue statistics of PC and FC are the same as Haar, just that in this one plot it looked similar. There's a lot more to try to check.
So sorry, Douglas, but would you expect that would you have a reason to expect that the eigenvalue statistics only get there if it's Haar, or is so in other words, is it surprising that you'd get there earlier with just a smaller amount of randomness?
Well, okay. My impression is, maybe this is wrong, is that PRUs and matrices with random matrix eigenvalue statistics are both kind of generic. Like if you don't do anything too dumb, like it's hard to prove, but like if you don't do anything too dumb, you're going to get them. And so I think of the eigenvalue statistics as one way of checking if you've done something dumb. So that was the logic behind why I asked whether the PC and FC are,
which I guess is the case for PF, but
right. So PF's definitely dumb, and the eigenvalues will pick up on that.
Right.
Yeah.
So like Henry, when you guys defined the PFC, right? I mean, there must have been a reason you did it, right? I mean, it could be that that's what you could prove, right? Or it could be that PC and FC didn't work. So there's also a question I was going to ask Fermi.
Sorry, what was the question?
Is there a simple reason, or never mind simple? Is PC or FC not pseudo-random?
Oh, I think for PC, it's like more plausibly pseudo-random than FC. Just because when you query a permutation, there is like more a sense in which it's actually recording XY, like it sends X to like the superposition over Y's and is like recording XY. And the problem is just that
doing phases, right?
What?
F is sort of flipping
Yeah,
the
F is
phases.
only doing phases. Like it doesn't seem like it's scrambling enough. And of course, yeah, maybe the Clifford helps somehow. It just seems really unlikely. At least it's certainly not going to work with the proof we have, but like, I don't know. And I imagine somebody who kind of understands the properties of stabilizer states better could maybe come up with a quick attack on the FC construction. But I think it's maybe more plausible that PC is secure. It is just that like in the purification, like this claim I needed to make about all these states being orthogonal to each other, conditioned on you having some distinctness. It's like very much not true when you only have P. Like there's like some weak pairwise orthogonality, and it's like not clear how you go beyond that. But it may be there. It's possible. But yeah, I would be quite surprised though if FC were secure.
Oh, great. We are probably at the end of our time, unless there's a pressing direction to go in. Maybe shall we call it quits? So thanks again, Fermi. That was a fabulous talk, and thanks for Vinod, Henry, and Douglas. Really, really fun panel. Thanks a lot. And next week, Andras Gillian is going to speak on these algorithms for open quantum systems. So see you then.
Thank you.
Thank you.
Right, see you.
Bye.